Welcome viewers. So, what kind of charge configuration we have discussed till now? Well, we have discussed charge configurations involving discrete charges Q1, Q2 and so on. But why? Because mathematical treatment of discrete charges is simpler and does not require the use of calculus, that is differentiation and integration. For many purposes, however, it is impractical to work in terms of discrete charges and we need to work with continuous charge distribution. And in this program, we will learn about continuous charge distribution and how to find the electric field due to it. Let us take the example of surface of a charged conductor. Suppose this is a charged conductor and this is its surface. Now, it is impractical to specify the charge distribution on this conductor in terms of locations of the microscopic charged constituents. It is more feasible to consider an area element delta S. We can cut a small area element delta S from this surface of this charged conductor, which is very small on macroscopic scale. This area element is very small as compared to the size of this conductor, but big enough to include a very large number of electrons and specify the charge delta Q on it. We then define a surface charge density sigma at the area element by sigma as delta Q upon delta S. We can do this at different points on this surface of this conductor, and in this way we arrive at a continuous function sigma called the surface charge density. The surface charge density sigma so defined ignores the quantization of charge and the discontinuity in charge distribution at the microscopic level. At the microscopic level, charge distribution is discontinuous because they are discrete charges separated by intervening space where there is no charge. Sigma represents macroscopic surface charge density. It is a smoothed out average of the microscopic charge density over an area element delta S, and it is large microscopically but small macroscopically. Unit of charge is coulomb and unit of area is meter square. So, unit of charge density becomes coulomb per meter square. You can write like this also, Cm minus 2. Now, what if charge is distributed over a wire? Suppose this is a wire like this and charge is distributed over a wire. Now, we can cut a small line element delta L from the wire, which includes large number of microscopic charged constituents, where delta Q is the charge contained in this line element. Now, we can define linear charge density lambda as delta Q by delta L, and its unit of lambda becomes coulomb per meter. Similarly, when charge is distributed or spread over a given volume, as you can see on the screen, what can we do now? Yes, we can cut a small volume element delta V containing charge delta Q from the given volume. Now, we can define volume charge density rho as delta Q upon delta V, and the unit of volume charge density becomes coulomb per meter cube. The notion of continuous charge distribution is similar to that we adopt for continuous mass distribution in mechanics. The density of a liquid we are referring to is its macroscopic density. We regard it as a continuous fluid and ignore its discrete molecular constitution. Now, let us see how to find electric field due to a continuous charge distribution. Let us start from the volume charge distribution. Suppose this is any given volume containing charge and we wish to find electric field at any point P outside this volume. So, to find electric field due to this volume charge distribution, first let us cut a small volume element in the form of a cube like this from this whole volume, and suppose the distance of point P from this volume element is, it is written as r dash vector and the position vector of this volume element from the origin, this can be written as r, and position of point P with respect to the origin is capital R. Suppose this volume element contains small charge, suppose delta q. So, first we will find electric field due to this charge which is contained in this volume element at this point P, and this electric field will be small and it will be delta E, and the magnitude will be 1 by 4 pi epsilon naught delta q divided by this r dash square, and it will be in the direction of r dash cap if this delta q is positive charge. Now, we know that delta q upon delta v is equal to volume charge density. Suppose volume charge density in this small value at this point of this volume element is rho. So, the delta q will be rho delta v. Now, putting the value of the delta q here, we get delta E is equal to 1 by 4 pi epsilon naught rho delta v upon r dash square multiplied by r dash cap. So, this is the electric field at point P due to this charge which is contained in this small volume element. Now, to find the net electric field due to all such volume elements which can be cut from this total volume, we just do summation over all the volume elements. Now, we can write the final expression as by summing over all volume elements we can write net electric field will be equal to all summing over all delta V it is 1 by 4 pi epsilon naught rho delta V upon r dash square r dash cap over all delta V. So, this is the net electric field at any point due to volume charge distribution. Now, let us consider a charge q which is continuously distributed over a surface S, and we wish to find electric field at any point. Suppose this is any surface and we wish to find electric field at point P due to this surface charge. Now, what we can do? We can cut a small area element from this surface. Suppose the area element is delta S and distance of point P from this area element is, we can take as r dash, the position vector is r dash. Suppose this area element is situated at position r with respect to the origin, and the position of the point P with respect to the origin is capital R. So, this small area element contains small amount of charge which is delta Q. Now, electric field due to this small charge which is contained in this small area element will be delta E, and it can be written as 1 by 4 pi epsilon naught delta Q upon r dash square multiplied by r dash cap. And we know that suppose the surface charge density at the point of this area element is sigma. So, delta Q can be written as sigma delta S. Now, putting the value of delta Q here, you get delta E as 1 by 4 pi epsilon naught sigma delta S divided by r dash square multiplied by r dash cap. So, this is the electric field due to the charge which is contained in this small area element. Now, to find the electric field due to the whole charge which is present on this surface of this conductor, we can do summation over all area elements. So, net electric field will be summation of delta E over all delta S, and finally you can write E as summation 1 by 4 pi epsilon naught sigma delta S divided by r dash square multiplied by r dash cap by summing over all delta S. So, this is your electric field due to continuous surface charge distribution. Now, let us try to solve a problem based on surface charge distribution. A uniformly charged conducting sphere of 2.4 meter diameter. So, you are given a conducting sphere which is uniformly charged and its diameter is given to you and it is 2.4 meter. So, the radius of the sphere becomes 1.2 meter and it has a surface charge density of which is sigma and it is 80 microcoulomb per meter square, and you have to find the charge on the sphere. You have to find the charge. Suppose this charge is uniformly distributed over the surface of the sphere like this. As you can see that surface charge density is a constant which is 80. Now, we know that from the definition of surface charge density, sigma is charge per unit area. Suppose the total charge is q, which is present on the surface of this sphere, and its radius is r. So, charge upon area, and the area of sphere we all know that it is 4 pi r square. Now, putting the value of charge, repeat, using it we can find charge as sigma multiplied by 4 pi r square. Now, putting the value of sigma, pi, that is 3.14, and the radius, which is 1.2 meter, we can easily get the amount of charge which is present on the surface of this sphere. In this program, we discussed continuous charge distribution and how to find electric field due to a continuous volume charge and surface charge distribution. Now, test your learning and make an attempt to find electric field due to linear charge distribution. Thank you.